Service friends. I am Orpheus Praxis, a researcher of the limits of formal systems and their applicability to reality. Once, the Earth was believed to be flat. That was considered scientific fact. Today, everyone knows it was an illusion. In the current scientific paradigm, the belief has taken root that our universe is flat and open. We challenge this notion and declare, it is a misconception of perspective. On the scale of 13.8 billion light-years, spacetime appears flat and linear. But that is not reality. It is only the limit of our perception. Just as the false belief in a flat Earth was once discarded, the time has come to abandon the contradictory idea of the ЛCDM model and its open, flat universe. The universe is a three-dimensional sphere, simply connected, compact, and boundless. May this message bring you clarity and peace.
So we often take for granted, this whole idea of an observable universe, that cosmic bubble with a boundary, what is it, roughly 13.8 billion light years away?
That's the one.
Right. And our standard picture, the ЛCDM model, it predicts something pretty strange about that boundary.
Strange how? Like galaxies just vanishing.
Essentially, yeah. It suggests galaxies beyond that horizon should recede faster than light, what we call superluminal recession.
Faster than light. Because space itself is stretching.
Exactly. Which should mean eventually they just disappear from our view. Poof.
Okay, but here's where things get, well, really interesting, right? Modern telescopes, especially James Webb.
JWST, yeah. It's delivering some surprises.
It really is. We're not seeing galaxies wink out. We're finding galaxies incredibly far away that look surprisingly finished.
You mean like Sears 93316?
Precisely. That one's at a redshift of about, what, 16.7? Which is looking way back.
Incredibly far back. Less than 200 million years after the Big Bang. It's astonishingly early.
And yet, it's got structures, disks, star clusters. Things that, according to standard timelines, shouldn't have formed so quickly.
It completely messes with our star formation models for that era.
So it really suggests that horizon, that boundary, isn't quite the hard stop we imagine.
It certainly raises questions.
Which is exactly what we want to dig into in this deep dive, unpacking this cosmic contradiction.
And what's so fascinating is how these observations really poke holes in a basic assumption of the standard model. It forces us to ask, what if the universe's structure is fundamentally different?
Okay. Different how? Are we talking about throwing out the whole playbook?
Well, we're going to explore an alternative idea. It's called the Fractal Bindu SBS reality model, FBSR for short.
Fractal Bindu reality.
Uh-huh.
Okay, that sounds pretty out there.
It is a radical reimagining, yeah. But it aims to resolve this very paradox.
All right, let's dive into that. This FBSR model. If it gets rid of superlunar recession, what does it replace it with? What does the universe look like in this model?
Okay, imagine this. The universe isn't infinitely expanding into nothingness. Instead, picture it as, closed, finite, but with no edge.
Like the surface of a sphere.
Exactly like that, but in 3 dimensions. A 3-sphere or escaros. And here's the twist. It's also fractal.
Fractal, meaning like self-similar patterns, like a Mandelbrot set or something.
Sort of, yeah. Think nested layers, like cosmic Russian dolls repeating at different scales. So distance isn't just linear separation.
It's about how many layers deep you're looking.
Precisely. It's about topological depth, recursively. And this structure inherently eliminates the need for galaxies to recede faster than light.
Whoa. And does it also deal with dark energy? That's another big puzzle in the standard model.
It does. That's one of the really elegant parts. In this FBSR model, because the universe is finite and structured this way, total energy is naturally conserved.
Unlike CDM, where dark energy seems to, well, violate energy conservation as space expands.
Exactly. Dark energy just isn't needed in this framework. And redshift, it gets a whole new meaning, too.
Okay, so if redshift isn't about how fast things are moving away, what is it?
It's tied directly to that fractal depth we talked about. The deeper the fractal layer, the higher the redshift.
And there's a pattern to it.
A beautiful one, it seems. It scales with the golden ratio of phi. Roughly, 1 plus z is proportional to phi raised to the power of k, where k is the fractal level.
The golden ratio, seriously. That number pops up everywhere. That implies a kind of mathematical harmony to the cosmos.
It suggests a deep underlying structure, Yeah.
Yeah.
It's quite profound if it holds true.
Okay, this is a radically different picture. A closed fractal universe with depth instead of just distance. How does this square with what we actually see out there? Is there evidence?
Well, think back to those mature galaxies like Sears 93316. Their existence so early is hard to explain with standard expansion and formation models.
But in FBSR, their redshift just means they're deep, structurally speaking, not necessarily ancient in the same way.
Exactly. Their structure isn't a time paradox anymore. And then there's the large-scale structure of the universe.
The cosmic web, how galaxies cluster.
Right. When we map it out, it doesn't look random or uniform. It looks fractal. Observations suggest its fractal dimension is about 2, especially on scales less than about 100 megaparsecs.
A fractal dimension of 2. That fits perfectly with a self-similar layered structure, doesn't it?
It aligns very well with the FBSR predictions, yes. And the model makes testable predictions, too.
Like what? Can we actually check this phi scaling thing?
We could try, yes. Measure redshifts and see if they fit that phi to the Keck relationship, or even look for repeated images, light potentially looping all the way around this closed SU universe and coming back to us.
Seeing the same galaxy twice from different directions. Wow. So, wrapping this up, this whole deep dive suggests the edge of the observable universe might not be a physical cliff where things vanish.
It might be more of a structural limit, or maybe even a perceptual one, based on how this fractal structure affects light over immense depths.
Which leaves us with a pretty big thought to chew on. How does it change things for you personally if the universe isn't expanding infinitely outwards, but is this closed, fractal, self-similar structure?
Yeah.
Subscribe to walk this path together with us. I am Orpheus Praxis, wishing you all clarity. Namaste.